Homework 5A. In question number 1, it gives you the molar volume for chloroform and acetone. All right, and also give you partial molar volume for chloroform and acetone. Molar volume is used for pure substance, and the partial molar volume for mixture. It asks you to calculate the total volume. The total volume is calculated by this equation. Okay, if it's pure substance, here is the molar volume. If it's mixture, then this will be the partial molar volume. Okay, so before mixing, they are pure substance, and therefore you use molar volume chloroform times number of moles chloroform, molar volume acetone times number of moles acetone, and this gives you the total volume of the two pure substances, and this is before mixing. After mixing, you use partial molar volume of chloroform, partial molar volume of acetone at this condition, that is the concentration. In this concentration, the partial molar volumes are given, and so the calculated volume is the volume of the mixture with that particular concentration. A container is divided into two compartments. One contains 2 moles of hydrogen, the other 4 moles of nitrogen at temperature T and pressure P. The question 1 express the total Gibbs energy before mixing. Before mixing, they are both pure substance. Similar to the total volume, total Gibbs energy is number of moles times molar Gibbs energy. Here, molar Gibbs energy is the chemical potential. So chemical potential for pure substance is the standard state chemical potential, that is 1 bar plus RT ln P divided by 1 bar. That's the pure chemical potential. So plug in here number of moles hydrogen, chemical potential of hydrogen, number of moles nitrogen, chemical potential of nitrogen, both at the pressure P. That's before mixing. Now after mixing, equation is similar, but the chemical potential are slightly different. The pressure should be partial pressure. These are for the mixture chemical potential of hydrogen and nitrogen. Okay, that's question 2. Number 2. Number 3, express Gibbs energy of mixing. So Gibbs energy of mixing is the difference between before mixing, after mixing, is the delta G. Okay, Gibbs energy after mixing minus Gibbs energy of before mixing, and you can see that both contains standard state 1 bar, so they cancel each other. Here also cancel each other. So what you get is RT ln. So let's write it. So it's for this one should be hydrogen times RT ln P standard state. Okay, that's after mixing minus before mixing, and that will be hydrogen RT ln P naught. Okay, so that will be N hydrogen RT ln. Now natural log A minus, so natural log A minus natural log B equals natural log A divided by B. And so that when you divide by that, the standard state cancel each other. So you get hydrogen partial pressure divided by pressure. Okay, this pressure is the pure pressure, the hydrogen before mixing the pressure. Now before mixing, both hydrogen and the nitrogen are pressure P. When you remove the wall, the two gases mix each other, and the pressure becomes the total pressure. So now this pressure is the total pressure of the mixture. So according to Dalton's law, the partial pressure divided by the total pressure in the mixture should be the mole fraction of hydrogen. In this case, it's the mole fraction of the hydrogen, and the mole fraction of the hydrogen should be 2 moles divided by 2 plus 4 is 6, and that will be 1 divided by 3. Okay, and therefore this should be N hydrogen RT ln mole fraction of hydrogen. So that's the first term. So let me erase this. Okay, all right, so that gives you this equation: nRT ln XA, nRB ln XB. So here, XA, A is hydrogen. So this is hydrogen, hydrogen, and this is nitrogen and nitrogen. And hydrogen is 1/3 XA, hydrogen, nitrogen is 2/3. And in fact, this is an equation that we derived in the class, and we showed that ideal gas mixing, this is always less than 0. So ideal gas mixing always is spontaneous. So plug in the data, and that you should be able to get negative 9.5 kilojoule. Question number 3. The vapor pressure of benzene is 400 torr at 60.6 Celsius. Note that this is the vapor pressure of benzene when it's pure. Okay, we use the star to represent pure substance vapor pressure. Now, when an involatile inorganic compound is added, the vapor pressure of benzene, here we should use PB. Okay, this should be less than the vapor pressure when it's pure. It asks you to calculate the final pressure. Okay, usually the final pressure of a solution should equal to the partial pressure of all different substances. But in this case, the other component is involatile. That means in the gas phase, this is 0. So all we need to do is just calculate the vapor pressure of benzene. And Raoult's law tells us that the vapor pressure of benzene should equal to the vapor pressure when it's pure times mole fraction. So this is 400. All right, that's 400. And in order to calculate the vapor pressure in the mixture, we need to calculate the mole fraction. Now we have grams, we have molar mass, all right, and also grams of benzene and the molar mass of benzene. So we calculate the number of moles. So this is the number of moles for the involatile organic compound, and this is the number of moles for benzene. And therefore we can calculate the mole fraction of benzene is number of moles benzene divided by total number of moles, and that gives you 0.965, and go into this equation. You can calculate partial pressure of benzene in the gas phase equals 386 torr, and note that this is less than 400, which is the pure benzene vapor pressure. Question number 4. Using Henry's law to calculate the solubility of CO2 in water when its partial pressure is given. In class, we showed that for very dilute solution, the pressure of a solute should equal to the mole fraction of the solute times Henry's constant. And this is called Henry's law. In this equation, mole fraction has no unit, and therefore the unit for K constant should be the same as the pressure, which is Pascal. Now there's another version of Henry's constant, Henry's law, that is PA should equals to, instead of mole fraction, we can use molality. Both are concentration, but molality is moles per kilogram of solvent times also a Henry's constant. Of course, these are different Henry's constant. So how do you know which one do we use? We look at the unit of Henry's constant. Okay, if Henry's constant is in Pascal or atmosphere, then we know it's this equation. But if the Henry's constant includes moles kilogram, then that's molality. That's molality. So in this question, the Henry's constant unit is kilopascal kilogram per mole, and that means we are using this equation. So here we calculate the pressure. All right, use Henry's constant times molality. So molality is calculated by pressure divided by K. So for pressure 0.1, because Henry's constant is in kilopascal, so we convert atmosphere to Pascal, and so here pressure divided by K constant, and that give you 3.4 times 10 to the minus 3 moles per kilogram. Okay, the question tells you to calculate solubility as a molality. So this is a molality. Every kilogram of solvent you dissolve 3.4 times 10 to the minus 3 moles of CO2. Similarly, when the pressure is 1 atmosphere, and using the same equation, you calculate the solubility increase 10 times. Okay, so in order to increase the solubility of CO2, you should increase the pressure of CO2. Question number 5. A dilute solution of bromine in carbon tetrachloride behaves as an ideal dilute solution. Now first, this question indicates bromine is a solute and carbon tetrachloride is a solvent. Solvent is the major component of the solution. Solute is the minor component of the solution. Now, the ideal dilute solution refers to a solution where the solvent obeys Raoult's law and the solute obeys Henry's law. And therefore, we can write these two equations. For carbon tetrachloride, which is a solvent, you use Raoult's law. The partial pressure equals the vapor pressure of A when it's pure times mole fraction. The vapor pressure for carbon tetrachloride when it's pure is this number, 33.85. Okay, that's the pure carbon tetrachloride vapor pressure. For bromine, the Henry's constant is given here. Okay. Now, in order to calculate the pressure, we need to know the mole fraction. The mole fraction given here, 0.05, is for bromine mole fraction. So how do you calculate the mole fraction for carbon tetrachloride? They add together is the 100%, so it's 1 minus xb, and that gives you 0.95. Okay, and therefore the partial pressure can be calculated. For bromine, it's 0.05 times the Henry's constant. For carbon tetrachloride, it's 0.95 times its own vapor pressure when it's pure, and that gives you 32.2. Added together, it's the total pressure. All right, one more thing is it asks you to calculate the composition of vapor phase. Now, composition is about mole fraction. we already know the mole fraction for the solution phase. We want to calculate the mole fraction of the gas phase. In order to distinguish between this mole fraction in the solution, mole fraction in the gas phase, we use X to represent mole fraction in the solution. So in the solution, the mole fraction XA, XB. In the gas phase, the mole fraction we are going to use is YA, YB. So this question is asked you to calculate the mole fraction YA, YB, the mole fraction of the carbon tetrachloride and the bromine. Okay, so how do you calculate the mole fraction in the gas phase? This has been studied in chapter 1, the gas phase, based Dalton's law, and that is the partial pressure of A times equals the total pressure times mole fraction. Okay, total pressure. All right, so these are all about the gas phase. In the gas phase, the pressure of A equals total pressure times mole fraction. So here total pressure is 38, mole fraction, it should be YA, okay, in the gas phase. And so YA should equals to partial pressure divided by total pressure. Okay, remember this equation, Dalton's law, is about everything in the gas phase. In contrast to the Rahul's law or Henry's law, where mole fraction here is the solution phase and the pressure is the gas phase. Rahul's law, Henry's law is a bridge between solution and the gas, but Dalton's law is everything is about the gas phase. So the gas mole fraction is the partial pressure of the gas A divided by total pressure. Using this equation, we can calculate the carbon tetrachloride mole fraction is the partial pressure, which is 32 divided by 38. Okay, so that gives you 0.94. For bromine is 6.1 torr. That's the that's this one divided by 38, and that gives you 0.16 partial mole fraction in the gas phase. The last question: when an involatile solute B is added to a pure solvent A, the chemical potential of A changes. It asks you to express the difference of chemical potential of pure A and A in the mixture. Now in class, we derived the equation for the chemical potential of the solution. So if you have a solution A plus B, okay, the chemical potential of A in the mixture should equal to the chemical potential of A when it's pure. Okay, that's pure A plus RT ln XA. XA is the mole fraction in the mixture. Okay, so this is the A in the mixture, and this is A when it's pure. And we can rearrange. So the mixture, A in the mixture minus A when it's pure equals RT ln XA. And therefore, this is the difference between the chemical potential of A when it's pure and the chemical potential of A in the mixture. The difference is RT ln XA. Okay, we can show that this is always less than 0 because XA is always less than 1. Okay, and therefore natural log is always less than 0. So this means that whenever you add impurity into a solvent, the chemical potential of the solvent always decreases. Okay, this is a pure A. All right, and so this when you add impurity, this is the chemical potential with impurity. And this minus the pure solvent is a negative number. That means the chemical potential of impure solvent is always less than the pure solvent. And this will cause the consequence of colligative properties that we are going to talk about in the next section.